everybody. We're just going to get started. Welcome to Nextiva's AI Paper Talks. This is our episode number 3. And today we're doing something a little bit different. We're actually going to have 2 speakers talk to us about this paper talk or this paper research called huBert Self-Supervised Speech Representation Learning by Masked Prediction of Hidden Units. So we're going to have Avneet Singh and Robin Stites walking us through this. It's going to be a really interesting AI paper talk. It's really complementary, and I'm really excited for you to learn. And please make sure that you take your notes. You can start posting your questions as we go through this paper talk. And then at the end, as always, we are going to have time for questions. These sessions are meant to be a discussion. So we encourage you to bring up your questions, bring up your comments, and have this discussion. So with that, I'm going to hand it over to Avneet. So please, Avneet, take it over.
Thanks, Ruth. Welcome, everyone, to the talk. I hope you'll find it useful. So in the talk, Robin and I will be sharing a bit about speech recognition systems, about phonemes, which are the fundamental units of sound, and in particular, huBert, which is a very recent paper and has made some great advances in the field of speech recognition and learning representations about speech. Next slide, please. So we'll first discuss a little bit of history about speech recognition and how it works. Then Robin, who has a background in linguistics, will help us understand more deeply about phonemes, and then we'll dive into huBert. Next, please. So the history of speech recognition started around 1922, when there's this little toy where if you just spoke the word Rex, a dog would come out. And what's really doing is it's recognizing sounds. The air part of Rex, which is about 500 hertz. And when it hears that, it activates and the dog comes out. Now, this worked mainly for male adults, as females and children, they had a different frequency for the word and sound of Rex. Next, we went to IBM, where they sort of had a calculator. So 10 sounds for 10 digits from 0 to 9, and 6 mathematical operations. The system required us to utter each sound separately, like 1, 5, 8, and so on. After that, we had ARPA create a data set and a competition which was won by CMU. This had connected speech, the kind that we use on a regular basis, had 1,000 words. This was followed closer to 80s by more statistical models. We had GMMs, we had HMMs, and we had a higher vocabulary, so 10K words. So then in 2010, Jeff Hinton, who's considered the father of deep learning, and his student Muhammad Abdul Rahman, they used a GPU and they tried to train the model to identify phonemes from sound. So that was the beginning of using deep learning in speech recognition. And by 2012, Microsoft had these systems in production. Next, please. So this is what an early system used to look like. So we had voice coming in. Now, if I'm uttering a phoneme and you're uttering a phoneme, Robin and Ruth are uttering a phoneme, we'll all end up using slightly different frequencies. So the model would adapt based on the speaker. Before that, the wave file would be featureized to have a spectrogram and MEL filters. And this would be fed into an acoustic model. So the acoustic model is one of the main components of the system, and it identifies the kinds of sounds, fundamental units of sounds, which you can call phonemes. And once those have been identified, we can then move to a decoder, and having identified the fundamental units of sound, we can then translate that into letters and words, or words, and then into phrases and sentences. So today, we'll be mainly speaking about this part, the first 4 columns that you see, starting from speech features to phonemes. Next, please. So essentially, the key part of an ASR system is to recognize phonemes or something similar. And Robin will help us understand what they are, how they're uttered, and so on. Over to you, Robin.
Thanks, Avneet. So as Avneet mentioned, I have a background in linguistics, so I'm hoping to provide some potentially useful information on the underlying linguistic features that ASR systems are ultimately trying to learn. Humans we're capable of producing and perceiving a really astounding variety of speech sounds, but these sounds are constrained in some way by the mechanism of our vocal tract. So I'm just going to give a very, very brief introduction to the realm of possibility in speech production, how these features are measurable and how we can see them in a spectrogram, and how language divides this feature space to produce meaningful utterances. So as Avneet mentioned, is a spectrogram. I have my laser pointer, yes. Okay. So in a spectrogram, we have frequency on the y-axis and time on the x, and the darkness of the markings corresponds to relative intensity of sound. In order to extract features for analysis in ASR systems, these spectrogram images are essentially pixelated to generate vectors for small times of frame containing values for about 10 to 20 frequency bins in this range. The top of the spectrogram shows the segmentation between the different sounds, the distinct sounds or phones that comprise this sentence, "She came back and started again." And I've added some labels up here in what's called IPA, the International Phonetic Alphabet, which is a notation system used by linguists to represent phones consistently across languages. So just from this spectrogram, we can see some of the particular challenges for ASR. Phones are not of a fixed length, so some of them are extremely short, and some of them are long. And especially in spoken English, there is absolutely no direct mapping from phones to letters. So let's go into a little bit more detail regarding how these various speech sounds are produced and how they map onto spectrograms. So we start with the vowel. There are two different kinds of sounds that humans are capable of making, vowels and consonants in speech. And a vowel is a sustained vocalization produced by the vibration of our vocal cords through an unobstructed vocal tract. So that means that our mouth and our throat are open, and we're producing sound with our vocal cords. So as these vibrations travel through the vocal tract, you can think of the vocal tract as like a tube. They also produce various resonant frequencies or overtones, and these are called formants. In this series of spectrograms, the formants are indicated by the arrows. They're, as you can see, they're bands of intensity. And each vowel sound, each one of these is shows a different vowel sound, has a different relative arrangement of these formant frequencies. And what causes these various formant arrangements is the relative position of our tongue and our lips. So here we have, these are again in IPA, we have the words heed, hid, head, and had, etc., etc. On the right, we have a representation of the space that phonologists use to locate these different vowels. And the vertical and horizontal axes represent the relative position of the tongue in the mouth. And as you can see in the caption, there's also an indication for the rounding of the lips. So again, as we produce vowels, the different vowels are caused by us changing the shape of our vocal tract while we're allowing the vibrations of our vocal cords to travel through that tract. Importantly, vowel feature space is not discrete. So all the vowels are located on a continuum of tongue position. This makes them extremely susceptible to shifts and variation, which is why the vast majority of dialectical differences within a language are vowel variations. And again, this poses a particular problem for ASR systems because vowel sounds vary widely from dialect to dialect. And onto consonants. Consonants are produced by creating some kind of obstruction in the vocal tract. These obstructions are produced by various articulators, which are shown on the diagram to the right. So for example, the G sound is produced by touching, the back of the tongue to the soft palate, G, G. The figure to the left shows a spectrogram of 3 words that begin and end with different consonants, but whose vowel sound is the same. So we have bab, dad, and gag. Because they are relatively brief and often noisy or percussive, consonants are much more difficult to identify in a spectrogram. In fact, the way they are most precisely identifiable is through their impact on the adjacent vowels. And as you can see, the surrounding consonants in this figure change the contours of the vowel formants at the beginning and the end. And finally, this leads to a discussion of the phoneme, which is a concept that ASR systems are have been dealing with, struggling with since their invention. A phoneme, formally defined, is a class of phone. It's a class of sounds that can be used to differentiate between words in a particular language, and that's really important. They create meaningful differences, and those sets of differences are different for different languages. So I've listed here a couple sets of what are called minimal pairs, which are used to demonstrate that two phones are regarded as different phonemes in a particular language. And I've chosen some English examples that are challenging for some non-native speakers because their articulation is objectively quite similar, but to us as English speakers, they sound very distinct. And similarly, the Hindi examples to an English speaker who doesn't have those divisions, they sound very, very similar. Avneet, would you mind saying these 4 words for us?
The first word is dal for lentils, or dal for a branch of a tree. The next 2 are kam, meaning less, or kam, meaning work.
Right. So thank you, Avneet. So in Hindi, vowel length is actually something that has a phonemic import. And in English, if I say I'm going to call you or I'm going to call you, it means the same thing. I mean, it might mean, slightly different implications, but it's the same word. And so the challenge for ASR systems is to find these meaningful divisions of the phonological feature space for a particular language, while being inclusive enough to accommodate for dialectical and speaker-to-speaker variation. So while ASR systems have generally been trending away from explicitly programming phonological features into their models, perhaps it might be useful to think again about how integrating known phonological distinctions might be helpful in improving model performance. And I think Avneet will continue to address this question in his discussion of the huBert paper. So back to you, Avneet.
Thanks, Robin. That was very helpful to get a deeper understanding of phonemes, which is a fundamental part of what an ASR system is trying to learn. So now we'll dive into huBert. Next slide, please. So there's sort of 3 key ideas why huBert is important and impactful. So one is it's discovering these fundamental units of sound, phonemes and triphones, without explicitly being told, because that would be an expensive task. So it's discovering on its own. That's one thing. The second key aspect of huBert is the fundamental journey of AI from statistical models, which would train on hundreds of data points, to machine learning models that would train on thousands of data points, to deep learning models that train on millions of data points, to reinforcement learning models that train on 10 to hundreds of millions of data points. So the journey is of having more compute power. That higher compute power allows us to have bigger models, more parameters, and that allows us to learn from more data, and that gives us better performance. So huBert could be considered as the next stage of Wave-to-Wake 2.0, and Wave-to-Wake 2.0 was about 300 million parameters. huBert is about 1 billion, so roughly 3 times more. And ASR systems are very good. They are better than human in speech transcription when the voice is clear and there's little accent and it's being spoken slowly. When it's noisy or there are a lot of accents, then the performance degrades dramatically. So huBert improves performance on the what is called the other data, dev other and test other in Libri speech by 19 and 13%, which is significant improvement. This data is more noisy. So that's the value that huBert adds. Let's see how it does that. Next, please. So huBert is inspired by the idea of BERT, which was built for NLP tasks. So BERT was trained on all of Wikipedia and Google Books, and it tried to learn a vector representation for a word. What huBert is trying to do is it's trying to learn a vector representation of a unit of speech. So the way it's done is, at the first layer, we have a wave file for sound. We break it into 25 millisecond time frames, and we run that through some convolution operations. Once that is done, then just like BERT, we take some of these 25 millisecond time frame units and we mask them. And then, so about 8% of them are randomly picked, and every time we pick one of them, that unit and the 9 units in front of it are masked. So this is our X vector that is fed into the transformer. The transformer now needs to learn to predict these masked units. To be able to predict these masked units, what it has to do is it has to learn 2 things. It has to learn some fundamental units of sound, and it also has to learn the temporal sequence relationships between these fundamental units of sound, so it can predict the masked units. And that's essentially what it is doing. So what the paper does is it takes the sound files, about 960 hours from Libra's speech. It featureizes them and creates spectrograms, takes 10,000 units, and it uses k-means as a way of discovering those fundamental units. So most languages have 40 to 60 phonemes and roughly 500 plus triphones. So in the first iteration, it creates 100 clusters, which is on the order of magnitude of phonemes. So we know what cluster each unit of sound belongs to. And we're asking the transformer to learn to predict that. So that's the problem formulation. Next, please. And they do it essentially with three models. They do it with base, which is 95 million parameters. They do it with large, which is 317. And then it goes to extra large, which is 964, or close to a billion parameters. Next, please. So in the first iteration, the k-means clustering is done on the original sound. And we use 100 clusters. We train the base model to predict those clusters. In the next iteration, we take the sixth layer of the model, and we'll share why that layer is picked. We do clustering on the sixth layer, and this time 500 clusters to represent triphones. And then we do the same training. And after that, we take the ninth layer of the base model, and we train the large and the extra large models. Next, please. So the loss function is essentially the transformer takes the featureized inputs, masked inputs from the convolution layer, and it has to map it to which cluster does that unit belong to. So that's our loss function. Next, please. And essentially what it is doing, it's trying to minimize the distance between the centroid of a cluster, EC, and the output of the transformer for that time unit, OT. And because they have different dimensions, there's a projection matrix A. So that's the function, similarity function, which is used as part of the loss function. Next, please. So this will train the acoustic model, which will learn a vector representations of something similar to phonemes and triphones. So once the acoustic model has taken a sound file, a wave file, and produced a sequence of phoneme-like vectors, then we use a CTC loss function and we map those to letters. And from those letter sequences, we pick the top, let's say 5. That's the log P CTCY by X. And then we also use a language model, which is learning as to what's the probability that certain words occur together, like new and York, a high probability, new and newest, probably low probability occurring together. So we use that, and we use the length of that sequence in the decoder to have the final transcription. Next, please. So if you look at these results, the CTC loss, the fine tuning was done on 10 minute, 1 hour, 10 hour, 100 hours. The huBert extra large tends to outperform most other models. Next, please. This is an interesting thing. So there are two kinds of techniques which are very popular in ASR systems. One is pre-training, which we just discussed, and the other is self-training, which is what Phil had shared in his previous talk. So they showed about models that do just self-training or just pre-training, and huBert extra large outperforms all of them. If we combine pre-training with self-training, then that performs better. So if we do self-training with huBert, the authors hypothesize that it will do better than the combo, because if we look at just pre-training, it has outperformed other pre-training models. Next, please. The other thing that they showed is they tried to figure out, is what huBert discovering as fundamental sound unit, how well does that correlate with what linguists consider as phonemes? So these are three metrics to look for correlation between phonemes and the fundamental units that huBert is discovering. Next, please. And what we find is that when we go from k-means of spectrograms and we move to k-means of the sixth layer, then going to the sixth layer provides better representations. Next, please. And we find that if you notice the last two layers in PNMI, they have much higher correlation between phonemes and the units that huBert discovered. And if you see the last three columns, we see a better word error rate when the units that huBert is discovering is more similar to what linguists call phonemes. So that's sort of the fundamental idea, is that phonemes are fundamental units of sound and speech. As Robin shared, linguists have been studying them for a very, very long period of time. Now, huBert discovered those units. It had a much larger model, about 1 billion parameters, and that allowed it to improve performance on challenging problems like noisy speech or speech with accents. So that was the contribution of this paper. And now Robin and I would be happy to answer any questions, and if I'm unable to answer some, hopefully Phil can help us out in answering some questions too. Thank you. Over to you, Ruth.
Thank you, Avneet. Let me just put the spotlight also on me so that everybody can see me. This was fantastic. So please, if you have a question, if you have a comment, you can use the emoji to raise your hand. I think it's called reaction, or you can just send your question to the chat. We really want to hear from you. As we do that, I have one particular question. Of course, you know, I am one of those people with an accent, but knowing that my first language is actually Spanish, and I don't know if this is something that makes sense. Would it be possible then, if we're focusing on phone names, that we kind of like use the same model and we just feed in the phone names from like Spanish? And would the model be really easy to pick on that? Like, how can we use the model to use a different language?
That's a fantastic question, Ruth, and something very important to the ASR community. So huBert was trained on 60,000 hours of unlabeled speech of English. We can take the same model and train it on unlabeled data on Spanish, and it would then discover the fundamental units of sound used in Spanish, and such work has been done for various languages. So huBert, one of the key contributions of huBert is that it makes it easy to learn speech recognition systems on different languages, which can then be used for ASR or other downstream tasks like detecting emotions, detecting identity, gender, and so on. That's my take. If Phil and Robin would like to add that, super welcome to.
No, I think you pretty much answered it. The other piece is the language model that's used in it would also, you know, need to be selected as a language model for Spanish. But the basic same approach could definitely be taken, and the benefit of being able to do pre-training, which means you don't need that huge raft of already labeled data, can really speed up the application to other languages.
Fantastic. Thank you. We have a question here in the chat. Let me read it to you. This one is from Alex. He says, do you think we should try to use this model for receiving transcription of voice messages? Can huBert model show better results than WAVE to VEC 2.0 if we try to fine tune it on our data?
Very good questions, Alex. So, yeah, this is the great part about having a linguist in our team. And one of the first things that Robin had pointed out is Libri speech is people speaking very clearly, reading a book. And that's a little different from how we communicate in our conversations. So voicemail could be slightly different, and phone conversations could be even further different. So as you suggested, Alex, if we pick our own data and we pre-train on that, then we would learn better representations for that data. So that is definitely more helpful. It should work better for our data. And for the second question, so huBert is 3 times larger model than WAVE to VEC 2.0. So if we give it huge amounts of data, it can learn them more easily. So in that sense, if we feed it more data and we train on that, I would expect huBert to perform better than WAVE to VEC. Anything Robin or Phil would like to add?
Only that it's early days. You know, huBert is new, and there's a lot more kind of empirical data, experimental results, experience in working with VoIP. And the other thing that you did mention is the application of noisy student training can and the self-training. A lot of the core benefits that you get in the transformer-based approach are really already there in VoIP. It's just this is a slightly refined and probably more sophisticated and more phonetically granular encoder. So I think it's definitely promising, but it's early days. This is brand new research. That's what's cool. We're talking about it.
I'd just like to underscore what Avneet mentioned about the difference between read speech and spontaneous spoken speech. I really think that it is a categorical difference that I think a lot of times is sort of glossed over or it's not acknowledged as much as it should be. In particular, with the model that we've been working on, one of the biggest things that this model has had to learn is the words and which they're not actually words, but they are utterances that people in spontaneous speech say all the time. And if your model hasn't been exposed to those kinds of verbal tics or false starts, it will it definitely runs into problems and it misinterprets them and it causes a lot of errors. And so if it gets exposed to more spontaneous, imperfect, full speech, we found that it improves model performance on voicemails, for example, quite a bit.
And I think related to that, we have a question. Does this work in real time or does it require post-processing?
So essentially, there are two ways of handling transcription. One is, as the speech is coming in, we detect periods of silence. We feed those through an acoustic model like huBert or wave-to-wake. And that will give proposed transcriptions. And that happens super fast, hundreds of milliseconds. So we can just take that as the output, and that's close to real time. Most voice-based systems take about a second to respond, so this is within that time frame. Now, while that transcription has been provided in the background, we can still run the lexicon, the language model, and further refine this and replace the original transcription. That takes a little bit longer. So in a sense, yes, all these, the system can be used online based on the way that we decide to do the decoding.
We have another question. Will this model work on different varieties of the English language, which I believe has to do with accents, British, American, Canadian, and I believe my understanding is that it will, but I'll leave it to you, Avneet.
Yeah, so there are two major challenges for the current speech recognition systems. One is dealing with those varieties as you mentioned, and the second is dealing with noisy speech. So the way to deal with those varieties has been to train separate models. Like you can have one model for speakers from northern part of US, some for southern, another model for east, another for west. So that is typically the approach taken. And the data on which huBert has been fine-tuned is from all the regions. So hopefully it has a bit of all of them, although an approach that would perform better would be to have models separately trained on separate regions. Anything that Phil or Robin would like to add?
Yeah, I would sort of qualify that answer a little bit. The size of the model and the volume and variety of the training data that it's provided can yield good enough performance in a single model. I think that, you know, if you want there is a trade-off. If you want to have the best possible model for, you know, people from Maine, then yeah, you're going to estimate a model. You're going to train a model, you know, based entirely on that. But if you gather enough data, it's very much like the phonemes. When Robin showed how the representation of a phoneme, which is ultimately at the encoder layer, that's what huBert is trying to do. Is trying to take that noisy, varied, different between me and you expression of that common phoneme, and essentially lay out enough clusters. And in fact, it may be not, you know, it's a little bit misleading to say that the clusters are centered on the phonemes. They're probably not. There's actually probably several of them that correspond to each phoneme. And with enough parameters and enough data, the model can actually learn that. It can actually learn that it can learn to be able to do a good job transcribing Ruth and Robin and you and me. But it's all a question of how you want to make that trade-off. How important is it to you to get, you know, very, very high fidelity within subpopulations versus trying to get a model that performs reasonably well across a wide range?
One question that I have as we wait for any others, it's, for example, in speech recognitions, and I'm talking like about Alexa, there is this part of calibration, right? Is that something, like, how is that handled? Is that something that it's handled at the individual level once you kind of like calibrate for a specific use case?
So you mean calibrating for individual?
Yeah, calibrating, for example, for my specific accent, tone of voice, you know, so that the system can recognize the way that I speak better than, you know, if I was somebody else.
Yeah, that in the models, these models, it sort of does come down to the same question as the previous one, which is, sure, if you wanted to feed enough data to fit a model that's just for you, you could do that. And in the context of Alexa learning basically to recognize commands, it's not the same. It's not the same problem as, you know, what we're dealing with here. If you know that you have the ability to sample and to sample in a very targeted way, a set of commands from an individual, then, you know, the software is going to benefit from that. But there is no analogous concept really here, other than the pre-training and fine-tuning, which are broader. They're not just for like an individual. But fine-tuning is, I guess the analog would be the fine-tuning. which is like what Robin referred to, the difference between people reading books and an actual natural speech.
All right, we have another one. Does the count of parameters have an influence on the performance and processing speed?
Yeah, in general, as we increase the number of parameters in a model, that gives us more capability to learn more from more data. So if we have a bigger model and we give it more data and require more compute power, it'll hopefully learn more. So that performance would increase. When we run it for inference, then because there are more parameters and there is more computation, so it increases the amount of time taken for that computation. So both of them come with a bigger model. Training, it can perform better in terms of metrics, but it'll also require more computation during training and inference time.
And we have another one. Okay, so this one is a comment and then a question. This one comes from Anna. So huBert can be used for automatic speech recognition like WAV to VET 2.0. The paper shows that the representations learned can be very useful for speech generation. Are we planning to build a generative spoken language model which is able to generate speech without any use of text, enabling textless NLP?
Well, let me answer that one. Textless NLP doesn't really make sense, but speech generation is a whole kind of a separate set of concerns. That you're right that the underlying representation that's learned in huBert could be valuable in speech production, and I would expect that technology, starts to get applied to speech production systems. I haven't actually seen examples of it yet, but as we've said at the very beginning, this is brand new research. But I think the point is definitely valid. Could be useful in speech generation, speech production.
I don't really understand why textless NLP doesn't make sense. Because, I mean, humans do it. Like, that's what babies do. Babies can't read yet or write, but they are processing language, and they can also, I think that was kind of the question, right? They process it, and then they can also reproduce it. So
yeah, okay. I think I misunderstood what Anna was asking. Yeah, textless, me in that sense, yes. That it could just go, you just completely acoustically generate the speech, and there is no side trip into the land of text. Yes, yeah. That 100% could work. Yeah, sorry, I misunderstood the question.
Fantastic, and thank you. And we have a last one. Is there more extensive algorithms for speech impairment for AI speech recognition that we know of?
Speech
impairment.
I didn't understand. Speech. So in other words, doing ASR when on source audio from people with problems in speech production. Is that right?
Yeah, correct.
Yeah. I'm not familiar. I don't know of active research in this area, but what I do, but that doesn't mean it's not happening. Probably it is. And the kinds of techniques that we're talking about that enable the models to be more resilient against variations in pronunciation and accents would seem promising to work in environments where people have, problems producing sounds.
Fantastic. Thank you so much, Phil. Thank you, Robin. Thank you, Avneet. And thank you, everybody, for joining another episode of the AI Paper Talks. We hope that this inspired you to either want to learn more or want to show up for the next one. You're like so excited, or like, wait, I need the other one. With that, of course, we have a bunch of people from Nextiva joining the sessions. We also have some people that are not part of this Nextiva joining. So, check out if you're interested in being part of the team. With that, any last words before we go? Phil?
I just want to thank Robin and Avneet and everybody who joined, and hope that at least we piqued your interest in diving into this stuff. There's a whole lot to learn, but it is exciting. It's an exciting time, and I think Avneet did a great job in showing kind of where we are in history, and I'm excited about where we're going in both Nextiva, but also the industry that we're getting now kind of back into bringing the human side of speech back kind of into focus, and that's exciting. So come on in. The water's fine. If you're interested in working on this stuff and you don't currently work at Nextiva, you know where to find us. Thanks.
Exactly. Thank you, everybody. Thank you, Avneet. Thank you, Robin, and see you next time. Bye.
Thanks, Phil.
Thanks.
Bye-bye.